In previous videos, we have learned that a servo is a device that has both a motor and a sensor in one device. And we've learned that a servo is useful because it allows us to not only control the velocity, but control the position of the device. Now, servos like these ones that we've used in class before have the motor and the sensor already connected together internally to the device. Whereas other kinds of servos, like this linear slide potentiometer that we use, or these motors with encoders like you would get from Pololu or any other source of motors that you can find online, they do not have the motor and the sensor already connected together to do the positioning. Now, on the one hand, this is a pain because it means that we have to do the control to set the position ourselves in our code that we write. On the other hand, this is a great opportunity for us because it means that we can change the way we write our code to adjust the kind of motion that we get with the device. You may have noticed that when we use these servos in class, the motion of the servos is very jerky. The servos move at more or less a constant velocity from the starting position to the ending position, and they come to a very abrupt stop. This results in vibrations of the end effector, and the motion is not very lifelike at all. In applications where we need the motion to be smooth for different kinds of reasons, if we want to eliminate vibrations or if we want the motion to appear more lifelike, in those cases we would like to program motion that's much more smooth and gentle rather than jerky. In this lab and in the couple of labs to follow, we'll be learning the basics of how to control the velocity and position of a servo when we get to write our own code that connects the motor and the sensor part together. This study of how to connect together the motor and the sensor to get better motion is a whole field of study in itself. This field of study is known as feedback control. So in this class, we'll just learn the basics. If you find yourself interested in feedback control, you can take whole courses just on the topic of feedback control. In today's lab, we're going to be doing the most basic type of feedback control called on-off control. To start out with this lab, let's get our circuit set up. We're going to start by wiring up our motor chip. Here's a circuit diagram showing what each pin of the chip should be plugged into. I'm also going to wire mine up in this video so that you can try and follow along here. But make sure that your circuit follows the circuit diagram. I'm going to start by plugging in my power from the external power supply to pin number 8. That's the last pin on the left-hand side of the chip. And I'm going to plug in ground from my external power supply to pin number 4 on the chip. So I'll count 1, 2, 3, 4 and plug in ground to that pin. Next, I'm going to take one of the leads from my motor and I'm going to plug it in to pin 3 on the chip. So I'll count 1, 2, 3 and plug that in there. And I'll take the other lead of the motor and I'll plug it into the third from the bottom of the chip. So I'll start at the last pin and count 1, 2, 3 and plug it in there. Next, I'm going to take 2 jumper wires that will be connected to the PWM pins on my PSOC. These 2 wires should be connected to pin 2 of the chip and the second from the bottom of the chip. So we're doing the same thing to the top of the chip as the bottom. When I plug this one in to the second from the top, I plug the other one into the second from the bottom. Next, I'm going to use this rail over here to be my 5-volt and ground rail from the P-sock. In other words, I'm going to take my P-sock and plug in VDD to the power side, and I'm going to plug in ground to the ground side. That way I can just take jumper wires from here to the chip and leave them plugged in. So I'm first going to connect ground. I'm going to take this jumper wire and plug it into the ground rail and connect this to pin 4 or pin 5 of the chip. So I'll count from the top, 1, 2, 3, 4, and plug it in there. Then the 5-volt signal will go to pin number 1, the very first pin on the left. So I'll plug that one in there. And lastly, I need to have a jumper wire connecting the top pin on the left to the top pin on the right. Now, double check your wiring and make sure that it follows the wiring diagram that is showing here. This is also a time when you can make use of the fact that you are working with a partner. Sometimes it's easier to find a wiring mistake for someone who didn't do the wiring. So if you did the wiring of this chip, have your partner look at your wiring and check it against the wiring diagram to make sure it's correct. Once you've got your wiring correct, let's go and write some code. Start by creating a new project. Make sure you select the correct device, and also make sure you select empty schematic. I'm also going to create a new workspace rather than add to my current workspace. The on-off control that we want to develop here combines two concepts that we've already learned how to do. We need to move the motor. That's what we learned how to do last time in class. And secondly, we also need to be able to read the sensor and use that sensor information to change the speed of the motor. And we learned how to do that previously in the Read a Potentiometer lab. Let's start by setting up the motor. Open up the digital menu and then Functions and find PWM TC-PWM mode. If you remember from last time, in order to move the motor both in the forward and the backward direction, we need to have two PWMs. So drag two PWM blocks to your screen. Next, we need to wire up the clock inputs of both of these blocks. Scroll down to the System menu and find the clock. Wire one clock to each of these inputs. Now open up the Ports and Pins menu and get a digital output pin. Wire one digital output pin to each of the line outputs. Now let's set the PWM settings. Double-click and go to the PWM tab. We're going to change the period to 100 and the compare value to 0. Remember that the reason why we do this is so that we can easily keep track of what the speed of our motor is. If we set the period to 100, then whatever we set the compare value to in our C code will be a percentage of the maximum speed. Click OK and then do the same thing to your other PWM. Set the period to 100 and the compare value to 0. Next, let's set the pins. Go to the CYDWR window, click on the port drop-down, and let's use pins 1, 1 and 1, 2 for this. Now, let's write some code. I'll start by deleting the comments and also the CY global int enable. Inside the main function, the first thing I'm going to do is enable or start the PWMs. Next, I'm going to write some code to make the motor move forwards and backwards. We're just going to do this to test to make sure that our wiring is set up correctly. If we write 100 to the first PWM, that will send full power to one of the 2 motor leads. At the same time, we want to write a value of 0 to the other compare, so that we will pull the second motor lead to ground. Next, we'll wait for a bit while the motor moves. Now to make the motor move in the other direction, we'll send full power to the second PWM while pulling the first lead to ground. Build your code and program the PSOC. Now let's connect the PSOC to our circuit. Make sure that your PSOC is set to run on 5 volts, not 3.3. Then take these 2 wires that we connected to pins 2 and 7, that is the second from the top and the second from the bottom, and connect those to pins 1.1 and 1.2, which are here and here on the PSOC. So I'll plug them in right there and there. The only other thing we need to do is we need to connect 5 volts, that is VDD, from the PSOC to this power rail, and we need to connect ground from the PSOC to this ground rail. So I'll flip the PSOC over, there's ground, and VDD is down here. So I'll take VDD and I'm going to plug it into this power, and ground will go to the ground rail, and then I'll give 5 volts from the USB port to my PSOC. Your slider should be shooting back and forth. If it is, that means that everything's wired up correctly and we can go on to the next part of this code. Feedback control requires us to read the value from the sensor and use that value from the sensor to adjust what we're doing with the motor. So to set this up, first go to Top Design, and we need to put in here the blocks that we need to read the potentiometer. Scroll up to the top and expand the Analog and then ADC menu, and get this sequencing SAR ADC. Drag one of those to the screen. Double click on this, and we're going to set its settings just like we did previously in the Read a Potentiometer lab. We're first going to set the VREF select to VDDA so that the largest voltage we would expect to get from the potentiometer is recorded as VDD from the PSOC. Now go to Channels, and let's decrease the channels from 4 to 1 because we only have one sensor to read. Next, change the mode from diff to single. That will allow us to read the voltage on this pin relative to ground rather than relative to some other voltage. Note that the resolution is 12 bits, and also note that in the General tab it shows us that the single-ended result format, that is the format that we have when we have single mode here, is signed. So this sensor will be read in a 12-bit signed value. Click OK. Now scroll down to Ports and Pins, get an analog pin, and drag one to the screen and wire it to the input. Next, go to CYDWR and let's set this pin to pin 20. That's the pin we'll use to read the potentiometer. Now go to the main.c file. We will start by adding the code to initialize the ADC, that is analog to digital converter. The next thing I want to do is start the conversion process. You'll notice that I have a couple of warnings here. That's just because I have not built the code since I placed the ADC block in the top design window. So right now, PSOC Creator does not recognize that I have an ADC converter block. After we build the code, these warnings should go away. Now, I'm going to create a variable to hold the value read from the sensor. This variable is going to be a 16-bit integer. Even though the value is read in 12 bits, the value is actually stored internally in 16 bits. We'll call this value sensor. Before we read the value from the sensor, we need to set this parameter that tells the ADC converter to not read a value until the analog to digital conversion is complete. Then we can read the value. We haven't done anything with this value yet, but let's go ahead and build the code right now to make sure that these warnings and errors go away. After my build, I still have a warning here, and I can see that I made an error in this line. It should just be ADC SAR SEQ1 start. So change your line to remove that one that I had that was a mistake, and then build your code again. If you have any other errors that haven't cleared up yet, go ahead and fix those errors. You should still have one warning that says sensor set but not used. That's okay. Clear up whatever other errors you have and then we'll move on. Now here's how on-off control works. We're going to set a target value for the sensor that represents a position that we would like the slider to move to. We're going to turn the motor on forward if the sensor value that we read is less than the target value. And we're going to turn the motor on backwards if the sensor value is greater than the target value. For this first test, let's try and position the slider right in the center of its range. Now, since the potentiometer is being read as a 12-bit signed value, that means the largest value that can be read is 2 to the 11th, or 2048. That means that the slider will be in the center when the sensor value is 1024. We want the motor to turn on forwards if the sensor value is less than 1024. So I'll put in an if statement that says if sensor is less than 1024, and then a curly bracket to start that if statement. And here we already have the code to turn the motor on forwards. The only thing I'm going to change here is my CY delay. I'm not going to put that in the if statement. Now, if the sensor value is not less than 1024, we can use the word else to account for that. In that case, we want the motor to move backwards. Then, at the end of this whole process, we want to have a delay, but we'd like to have a pretty short delay. Now, build this code and program the PSOC. Now, we have to plug in the potentiometer. In order to do this, we need to know which of the leads is the wiper. Take a multimeter and set it to measure ohms. And with the two leads of the multimeter, take the one lead that's by itself on the potentiometer. Here's the one lead by itself on mine, and touch it to one of the multimeter leads, and take one of the leads on the other side where there are two and touch it with your other end of the multimeter. While you're holding these two leads, slide the slider. Here, my resistance is staying constant at 10 kiloohms as I slide the slider. That means that neither one of the two wires that I have is the wiper. So I'm going to take these two and plug them into power and ground. And it doesn't matter which one I plug in which way. Or rather, it does matter, but right now we don't know which is which. And so just plug one into power and the other into ground. The last one, which is the wiper, plug that one into pin 20. Now let's test our code by plugging in the external power supply. When you plug in the external power supply, one of two possible things will happen. Mine, just the slider shot to one side and just stayed there. However, if yours does this, I want you to notice something. If you pull the slider back with your finger, when you get to the center position, the slider will all of a sudden shoot to the other side. So if I do this again and I push it towards the center, it'll shoot to the other side. This is happening because the slider, instead of being attracted to the center position like we want it to be, it's being pushed away or repelled from the center position. You can fix this in two different ways. We either need to switch the leads on the motor or we need to switch the leads on the potentiometer. For me, it's easier to switch the potentiometer leads, so that's what I'm going to do. I'm going to take the potentiometer lead that's plugged into power and the potentiometer lead that's plugged into ground, and I'm going to swap them. When I do that, the second thing that could possibly happen happens. The slider goes to the center position, but it vibrates like crazy around its center position. I'm going to unplug this so we get rid of that noise. Can you see why this happened? Why it's vibrating like crazy around its center position? In controls terminology, this is called instability. Let's look back at our code to understand why this happens. Here's what we're telling the slider to do. If the sensor is less than 1024, that is, if it's 1023 or less, we're going to turn the motor on at full power forwards. Otherwise, we're going to turn the motor on at full power backwards. There's no place in this code where we get the motor to stop and just stay at its position. Let's add something into our code to get it to stop and stay at its position. First, rather than just checking if it's less than 1024, let's give it a little bit of a buffer zone. Let's try and get the motor to stay in its position if it's within about 5 counts of the center, both below or above. So we'll have a total buffer zone of 10 counts. So I'm going to subtract 5 from this and say that if the sensor is less than 1019, then we'll turn the motor on full speed forwards. Now, instead of else, we're going to say if the sensor is greater than, and here I'm going to add 5 to 1024. So if the sensor is greater than 1029, then we'll turn the motor on full speed backwards. Finally, else we'll stop the motor. And I made a mistake here. I'm going to go back and make this say else if. Now, to test this code, plug in the external power supply. My slider was already in the center, so it didn't move anywhere. Try pulling it away and letting it go. You'll notice that it's still unstable. We didn't make much of a difference. There's one more thing in our code that we need to fix to improve this situation. Back in the code, at the end where you have a CY delay, let's make this much shorter. The motor moves so quickly that waiting just 10 milliseconds at the end allows the slider to overshoot its position every time it goes to its target. Let's try and make this loop run faster and see how this changes the behavior. Let's see what happens now. Mine is still unstable, although less than it was before. Yours might be doing just fine now. It depends on which slider you have and what kind of power supply you have. If yours is still unstable, let's go back and I'll show you what else you can change to get it to be more stable. There are two things we can change to make it more stable. One thing we can change is we can give a wider buffer zone to the center. Instead of checking to see if the sensor is less than 1019, let's check if it's less than, say, 1010. And instead of checking if it's greater than 1029, let's increase this to, say, 1035. Let's see what this does. Now, when I pull back the slider and let it go, it's only unstable for a short time, and it comes to a stop. Let's see what else we can do to increase the stability. Last time, what we changed to try and increase the stability is we reduced the precision of the slide. We gave a wider buffer zone so that the slider could be less precise and still come to a stop. The other thing we can change is we can make the slider slower. Instead of moving at 100%, let's change it to move at only 80%. Test it by plugging in your external power supply and then pulling back the slider and letting it go. You can see that this is much more stable. Now, it hardly overshoots at all when it gets to its target position. Motion control is a big trade-off between speed, accuracy, and stability. We can make our positioning more stable by reducing the speed or reducing the accuracy. And along the same lines, if we try and increase the accuracy or increase the speed, we might have to give up some stability. We can increase all three of these, speed, accuracy, and stability, by using different kinds of control strategies. In today's lab, we use the control strategy called on-off control. Next time, we're going to be learning a new control strategy that's called linear control. Specifically, we're going to be looking at proportional control, which is one small part of a larger type of control called PID, or proportional integral derivative control.